The fourth factor is orbital. What orbital is the negative charge in? For example, compare the following compounds. Let's compare ethane to ethylene to acetylene. Ethane has a hydrogen atom right here. It actually has 6 hydrogen atoms, 3 on this carbon and 3 on this carbon. If we pull off one of the hydrogen atoms, we get the following carbanion. If we pull a proton off of ethylene, we get this carbanion. And if we pull a proton off of acetylene, if we pull this proton here off of acetylene, we get a negative charge like this. So if we want to compare the acidity of these 3 compounds, we have to compare the stability of these 3 conjugate bases. Now, we use our 4 factors. Factor number 1 says what atom is the charge on, and in all 3 cases, it's a carbon atom. Carbon, carbon, carbon. So factor number 1 doesn't tell us anything. We move on to factor number 2, resonance. Resonance also doesn't tell us anything. None of these are resonance stabilized. We move on to factor number 3. Are there any inductive effects? And in this case, there are no electronegative atoms inductively withdrawing electron density and stabilizing any one of these 3. So the first 3 factors do not give us an answer. We move to the 4th factor, which is orbital. Recall that a carbon with a negative charge is a carbon with a lone pair in an orbital, and that's what gives us the negative charge. Carbon has only 4 valence electrons with which to form its bonds and lone pairs, but we see here it has an extra electron. It's using 1 for this bond, 1 for this bond, 1 for this bond, and then 2 more. It's using 5 electrons for its bonding structure, but it's only supposed to have 4. So it's got that negative charge. But notice that we've got this lone pair in an orbital. And the question is, what kind of orbital is it in? In the conjugate base of ethane, the lone pair is in an sp3 hybridized orbital. In the conjugate base of ethylene, the lone pair is in an sp2 hybridized orbital. And finally, in the conjugate base of acetylene, the lone pair is in an sp hybridized orbital. Now, these orbitals are similar in shape, but notice that an sp hybridized orbital is closer to the nucleus. In the sp3 hybridized orbital, the electron density is farther away from the nucleus than in an sp hybridized orbital. So in an sp hybridized orbital, the electron density is closer to the positively charged nucleus and therefore more stabilized. Whereas in an sp3 hybridized orbital, the electron density is farther away from the positively charged nucleus and therefore is higher in potential energy. So, this negative charge is the most stable of these 3. This conjugate base is more stable than either of these, which means that this compound is more acidic than either of these. In fact, if we compare the acidity of these 3 compounds, pKa of acetylene is 25, the pKa of ethylene is 44, and the pKa of ethane is 50. Now remember that each of these pKa units represents 1 order of magnitude. In other words, saying, if we compare ethylene and ethane, ethylene is not 6 times more acidic than ethane. It is a 1 with 6 zeros times more acidic. It is 1,000,000 times more acidic than ethane. The difference in pKa between acetylene and ethylene are 19 pKa units. That's a 1 with 19 zeros after it, which is 10 billion times more acidic than ethylene. So acetylene is significantly more acidic than ethylene, and it's because of this effect with the orbital. The negative charge, the electron density, is closer to the nucleus and therefore stabilized.